we are going to go back to the beginning of the packet, and we're going to look at something called Riemann sums. So this is page 2. So basically, last class we were looking at how to find specific area under the curve using geometry. There are many times when we are given some sort of curve that does not fit any specific geometric shape, like this curve that we have right here on that page. We have a table of values here to go with that. So we know some points on the curve, but we don't know the equation of the curve. We don't know the exact shape. We just know a few points. And so it's still valuable to know the area under this curve, again, because the context might be, this is the velocity graph, and we want to know our displacement. Or this might be some sort of rate in gallons per minute of some kind of leak or something, and we want to know how many gallons we lost. So it's good to know the area under the curve. So there's ways to estimate the area under the curve using these things called Riemann sums, and they're just named after this guy named George Riemann. So if you invent something, you get to name it after yourself. Those are the rules. So thank you, George, for your contributions. So there's a few kinds of Riemann sums, and they tell us different things. There's pros and cons to both. But so we're working with this table right there, so we're kind of limited to that information. The first type of Riemann sum is called a left-hand Riemann sum, and so what that means is we're kind of drawing our rectangle starting from the left. So we'll see what that means right now. So I see. I'm using these x values 0, 2, 4, 6, 8, 10, 12. That's what I have on the table. So if I draw my first rectangle here, I start at the point 0, 1. The next value I know is at x equals 2, so I just draw a rectangle going all the way over to x equals 2. You can shade it in just for fun. Our next rectangle, we start at the point 2, 3. So that's the left side of that rectangle, and we draw to the right to x equals 4, because that's the next point that we have. And we keep doing that here. So our next point is 4, 4.3. That's the left side of our rectangle, and it goes to 6. Again, I'm not just making up these numbers, I'm using the table. Can't do this without a table. Or a function. And we go to 6, 5.4, which is right there. And we keep going. So there's the next one. 10, 7 is right there. And this curve, I guess, needs to go a little bit more over there. So I'll just draw it over there. Got a little bit more to scale. So we've got some rectangles in there, and we can see that this is not going to perfectly tell us the area. Is this going to be an underestimate or overestimate? This is going to be a pretty severe underestimate, as we can see here, but that's okay. But what we can say here is the integral of f of x from 0 to 12, and we can do this little squiggle equal sign. And basically, we're just going to add up the area of these rectangles. And what I'll tell you is, usually we won't have a calculator, and so usually we don't have to simplify finding the areas. So, for example, the first rectangle, we'll just say has a area of 2 times 1. The next rectangle has an area of 2 times 3. The next one has an area of 2 times 4.3. And we're going to do that for each rectangle. So how many rectangles are there? 6. So we want 6 areas. And that will be our final answer for this. Whoa. So we could say that. Sometimes we won't use the integral symbol. We'll just say LRAM equals. That is the abbreviation for left Riemann sum. Each of these rectangles has the same width. What's the width of all the rectangles? 2. So for this one here, we could also write it like this. This will not always be true that all the rectangles have the same width. But anytime they do have the same width, we can shorten our, write a little bit less, really, is how I would say it. Turn to your neighbor. How would we get a better estimate using this method?
Yeah, each interval.
Yeah, less width of the rectangle.
Yeah.
And the smaller it gets, the more it approaches the actual
Okay, so if we wanted a better estimate using this method, what would we ideally do? Use smaller rectangles. Rectangles, just smaller? And more, yes. Okay, so yeah, you can imagine the smaller these rectangles get, the more of them that we have, the better our estimate is going to be. Okay, turn to your neighbor. What determines how many rectangles we use and how big the rectangles are? What determined that for this problem?
the width, like the interval in between each x value.
Mm-hmm. Yeah. It's like 0.5, 1, 1.5, 2, 2.3, 4.
Yeah, the summation between each like point.
Okay, so what determines how many rectangles and how big they are? The coordinates, yes, from where? The table, yeah. Yeah. So this table, we needed that. With that table told us, okay, we have x values that are every 2, and we know those y coordinates, but that's all we know. So that's as many rectangles as we can do. We're limited to that. We would do more if we could. If we knew the exact geometric shape, we would rather do that. But this is what we have. So that's just what determines it. It's just the information that we're getting. Okay, so let's go to the next page here. So there's also a right-hand Riemann sum. And so I'm going to make sure that my graph is a little more accurate there. So these just mean that we start our rectangles from the right. So we start at this point here, 12, 7.5, and we draw our rectangle going to the right until we have our next coordinate. And then we just, from the right side of the table to the left, we just work our way left. So next I go to 10, 7, and I draw over to x equals 8, and so on and so forth. So you guys can go ahead and do that along with me. Okay, so once you've done that, fill out the expression here. What would the R ram equal? What does the right Riemann sum equal? And you don't have to simplify it. Do 2 expressions like we did on the last one. All right, did we get this? Both of these? So again, this bottom one we can only use when all the rectangles have the same width. All the rectangles or trapezoids, because spoilers, we're going to learn how to do a trapezoid estimate in just a sec. But they need to all be the same width, so you always have to double check. I can see in that table right there, it goes 2, 4, 6, 8, 10, 12, because it's the same table, but like, for example, 2 pages from now, if you look down at number 84, on that table there, what do you notice about the x values? Yeah, it's not the same amount of distance between each one. It goes 0, 3, 5, 8, so it's plus 3, plus 2, plus 3. So for that one there, we'd have to do separate rectangles. So we could not do it that way. We would have to do it the top way. So just always be on the lookout. So we can see this is overestimating or underestimating? Overestimate, yeah. Okay. And notice just as you're making these, what y coordinate did we not use for this one? 1. And for this one, the left Riemann sum, which y coordinate did we not use? 7.5. Yeah. So for the left Riemann sum, you never get to the far right one. You start on the left, you don't use them all, and it's the reverse for a right hand Riemann sum. Okay. Now, for a midpoint Riemann sum, if we wanted 6 rectangles, if you have pencils so that you can erase what I'm about to write here, you could follow along, or you could just watch. If we wanted 6 rectangles, they would still be the same width of 2. And what we would do is we would plug in 1 for x, and we would get that y coordinate, and we would make our rectangle based on the number 1, because it's between 0 and 2. To have a width of 2, we would use 1. And then we would plug in 3 for x, and we would use that y coordinate, and it would look like this. And this would actually be a pretty good estimate, because you see it's overestimating on one side of the rectangle, underestimating on the other side. What's the problem with attempting this right here? Yeah, we don't know. We only know the even x coordinates. Okay, so we're always limited by the table. So we can't do 6 rectangles. How many are we going to do? 3. We're going to do 3. So it says it right there, but the reason why is because we don't have enough x coordinates. So we're going to have some big fat rectangles that have a width of 4. And so which x coordinates will I use to determine the heights?
So when you're determining like the width, is it just you take it and divide it by 3?
Yes, yeah, I take the total distance, 12, and divide it by 3. Yes. Yeah. So what x coordinates will I use for the height of these rectangles? 2, 6, and 10, yes. So those are midway through these big old rectangles that we got. So I set my width there. I divide 12 into 3 parts evenly. Go to 6, go to the height, and just draw sideways from there. And then 10's up there, so it looks like that. So I'll just make a little note down there that we don't have the necessary x values for 6 rectangles. So our midpoint Riemann sum is just 4 times 3 plus 4 times 5.4 plus 4 times 7. Or in this case, because they all have the same width,
Is this more accurate in this case because there's only 3 rectangles? Like, than doing the right or left?
yeah, this definitely appears to be a way better estimate than either of the previous 2, even though there's only 3 rectangles. Yeah, because we're overestimating on one side and underestimating on the other. Turn to your neighbor. Would this give us an overestimate or underestimate based on the shape of the graph here?
We don't know. It's just like green. Or I mean, I feel like they should be like equal on both sides if the graph is right, but we don't know like technically the in between. So
I think maybe over. Sure, like very little.
yeah, maybe a little bit over.
Okay, what do we think? Overestimate or underestimate?
When we do this, are we just gonna be getting the table?
You'll almost always have a table.
Will we get the graph or just the table?
Sometimes just the table. Yeah, usually just the table. Yeah. Sometimes you gotta kind of sketch your own graph. Yeah. Overestimate or underestimate? Who thinks over? Who thinks under? Okay, if we look at this graph here, this graph, I can tell, is both increasing and concave down by the shape of it here. And so what I'm seeing is that this area is bigger than this area because it's concave down. So this is going to be an overestimate because basically the amount that it's going over is not quite as much as it's compensating for on the other side. So like this area, this over area is bigger than that one right there. You don't need to memorize like that a midpoint Riemann sum overestimates if it's increasing and concave down. You don't need to memorize that. There is a thing that you need to memorize that I'll tell you in a sec, but it's not that. This you just want to be able to look at and be like, oh yeah, I can see from the shape of the graph that would be an overestimate. Okay. Last but not least, we have a trapezoid Riemann sum. This is usually going to be the best one. This was actually invented later, I believe, it's actually not called a trapezoid Riemann sum. It's just called the trapezoid method. So I don't think George Riemann invented this one. So we just call it the trapezoid method. But basically what it involves doing is drawing little trapezoids. And it uses all of the y coordinates. And as we can see here, let me shade a different direction there. As we start drawing our trapezoids in, it's pretty dang close to that curve. It's not going to be perfect. Okay, so there's two different ways of writing the trapezoid area formula. It's the same thing, just kind of whatever one feels easier to memorize. I always think of the first one as the average of the bases times the height, but you can also think of it the second way. It's really tomato, tomato. With these trapezoids here, I'm going to do an exaggerated version so that we can see. These are all right trapezoids that are on their side. So the height is going to be the distance between the x's. And base 1 and base 2 are going to be the two different y coordinates. So our first trapezoid, that's how we would represent the area. Base 1 plus base 2 over 2 times 2, if you use the top way. You could also use the bottom way. You can do parentheses if that helps. It doesn't matter as long as you write it correctly. We're rarely going to have to actually calculate this. Sometimes we will, but rarely.
Because it's 2 divided by 2 times 2. Can you show it like 1 plus 3?
Yes, yeah. If I wanted to just write 1 plus 3, that's fine. I would always recommend for these, leave it in the most unsimplified version that you need to. So for an FRQ, you can just write out like all the areas separately. And so just to avoid, I don't know, double canceling something out by accident or making a mistake here, like that's what I would recommend. But yeah, if we actually had to actually evaluate this, we would like the height and the divided by 2 are going to cancel for every single trapezoid here. Yes. What we want to be on the lookout for always is trapezoids that don't have the same height. So go ahead and write out all the trapezoid areas for those. Okay, so if we do separate trapezoids, it's going to look like this. We will frequently have to do it this way because it's very rare that actually you're given a table where all the heights of the trapezoids would be the same. So you just always be ready to do always be ready to do separate trapezoids. But there are simpler ways we could write this because of what David pointed out, the 2's will cancel for all of them. Our area could just be written as, well, we don't even need parentheses now. 1 plus 3 plus 3 plus 4.3 plus 4.3 plus 5.4 plus 5.4 plus 6.3 plus 6.3 plus 7 plus 7 plus 7.5. We can write it that way. Or if you notice, every number is repeated except for which ones? Yeah, the first and last. So we could, the shortest way to write this would be 1 plus 2 times 3 plus 4.3 plus 5.4 plus 6.3 plus 7 plus 7.5. So there's just different ways to write it. On an FRQ, it doesn't matter if they're all the same. Write it however you want. But be ready to do this one the most. Just individual trapezoids added up. Okay, let's go to the next page. Okay, so for this one right here, we can do Riemann sums when we don't have a table, if we know the equation of the function that we're using. So we know x squared we could sketch a little graph of x squared right here. And for the first one here, if we're doing left Riemann sum, we're doing 4 rectangles. What do our x coordinates need to be? Turn to your neighbor. What do our x coordinates need to be for 4 rectangles? Okay, so we need 0, 1/2, 1, and 3/2. Agree? Okay, if we're doing a right Riemann sum, what x coordinate do we need that's not on here? 2. And which one would we not use? 0. So maybe it's good to just make one table of values now that we could use for all 4 of these. Okay, I'm gonna put you guys in random groups to do this. All right, as you guys are finishing up, I'm just gonna sketch the rectangles up here. All right, let's check these here. So for the left hand estimate, since all the rectangles have a width of 1/2, we could put 1/2 on the outside. And we want to do 0 plus 1/4 plus 1, which I'll write as 4/4, plus 9/4. And so that I got that to be 1/2 times 14/4, which is 7/4. Did you guys get that for the LRAM? 7/4. Okay, and that's like 1.75. So we need to compare that later. For the RRAM, it's 1/2, and then we go the reverse order here. 16/4 plus 9/4 plus 4/4 plus 1/4. And I got that to equal 1/2 times 30/4, or 15/2, which is 3.75. You guys get that? MRAM, the rectangles both have a width of 1, so it's just 1 times 1/4 plus 9/4, so that's just 10/4. Or 5/2, or 2.5. The trapezoids method here. So each trapezoid is going to have base 1 plus base 2 over 2, and then has a height of what? Yeah, it's a height of 0.5 or a height of 1/2. So if I wanted to factor out the divided by 2 and the times 1/2 for the height, there would be a 1/4 on the outside. and then it'd be 0 plus 1/4 plus 1/4 plus 4/4 plus 4/4. We have 9/4 2 times, and then we have 16/4 on the outside though. So I got this to equal 11/4, which is 2.75. You guys get that? Yeah.
For the right one, I think it says 15 hours.
Which one?
Like the right.
Oh yeah, 15/4. Sorry. Yeah, 15/4.
Oh, he did it different. He's
Yeah. Sorry.
I asked like a dumb question, but do we have to write 0 radius there?
No, you don't have to. No. Okay, for the integral that represents the actual area, this is what we were learning about last time. So that's integral of x squared from 0 to 2. Make sure you have dx on the end. You need that always. Do you guys remember how to do this on the calculator? It's math and then what option? 9, yeah. Or, whoa, I don't know what's going on here. Something crazy. Hello? Okay. So I got this 8/3. Did you guys get that?
For my calculator, I would
Look on page 6. So you do the function, so x squared, comma x, comma 0, comma 2. Yeah, Sarah.
How do you make it a fraction?
If you press math and then enter, it's the first option there. Okay, so then the trapezoid method is the closest, which it usually will. Okay. One thing that we are going to want to memorize here is on the next page. Actually, let me show you this. Where is it? Hello? Here it is. I think you guys know Brandon Roller. He graduated a few years ago, but he made this for me. He was in my calculus class. So if here's a curve, and we're doing left-hand Riemann sums. So as we can see, when this curve is increasing, the left-hand method is underestimating or overestimating? Underestimating, right? So it's got these big gaps there. But when it's decreasing, the left-hand estimate is going to overestimate. That is something that you want to memorize or at least understand really well. Of course, and what's cool about this one here is I can add more subintervals or fewer. It's a little silly looking. But then if we do right hand, so right hand is reverse. When our function is increasing, our right hand estimate is overestimating because it's pulling all the numbers to the right, right? So it's like the higher numbers as it comes back. But when we're decreasing, the right hand method is going to underestimate. You don't have to memorize those connections for midpoint or trapezoid. If you may figure them out, but these are the ones that we want to memorize. We can just look and see midpoint, Riemann sum. Whether it's underestimating or overestimating depends on both, whether it's increasing or decreasing, and the concavity. So you have to kind of compare two things. So usually you can just look and figure it out. You'll never be asked really though. Trapezoid, Riemann sum looks more like this. This one is just based on concavity. So if a function is concave down, it's going to underestimate. If it's concave up, it'll overestimate. But you don't have to have that memorized. You can just kind of picture it and see. But the first two you want to have memorized. Okay. I think we don't have time for the other thing that I wanted to do. That's okay.